Mean value theorem. If a function f is continuous over the interval a to b and differentiable over the same interval a to b, then there exists a point c within that open interval where the instantaneous rate of change equals the average rate of change over the interval. In other words, f prime of c is equal to f of b minus f of a over b minus a. So, all this is saying, if you have a graph here, right, that's differentiable and continuous, if you get the average rate of change between the interval a to b, there's going to be at least one point c in between where the instantaneous rate of change is equal to the average rate of change. So you see at this point right here, you can see if you drew the tangent line, it's parallel or the same as the average rate of change. There's also one other point right here. In this case, they're only guaranteed one, but in this case, there's more than one. You can see right here, if you drew another tangent line, the instantaneous rate of change is equal to the average rate of change over the interval. So let's do some practice questions here. Use the function f of x is equal to negative x squared plus 3x plus 10 to answer the following. On the interval 2 to 6, what is the average rate of change? They're just asking for the average rate of change. So that's just f of 6 minus f of 2 over 6 minus 2. And that's equal to, we plug in the 6, negative 36 plus 18 plus 10 minus parentheses, negative 4 plus 6 plus 10 all over 4. And this actually gets us a negative 20 over 4, which is negative 5. That's the average rate of change of this function f of x on the interval 2 to 6. So on the interval 2 to 6, when does the instantaneous rate of change equal the average rate of change? So when does the instantaneous rate of change equal the average rate of change? So to get the instantaneous rate of change for the function, just find the derivative, which is negative 2x plus 3, and then you just set it to the equal to the average rate of change, which we calculated to be negative 5 right there. Negative 5. So now you can just solve for x, subtract 3 on both sides, negative 2x is equal to negative 8, divide both sides by negative 2, and you get x is equal to 4. So when x is equal to 4, the instantaneous rate of change is equal to the average rate of change for this interval. So MVT versus IVT. In the past, we learned IVT in 1.16. IVT does not deal with derivatives. It's just with continuity. See, IVTs on a given interval, you'll have a y value at each of the endpoints of the interval. Every y value exists between these two y values at least once in the interval. So pretty much, as long as you have a continuous function here, like if you start like on the second floor of an elevator, and at the 8th floor on the elevator, you're guaranteed to have passed through any floor in between. You're not dealing with derivatives for IVT. No derivatives here. But for MVT, that's with derivatives. The derivative must equal the average rate of change somewhere in the interval, which is what we just worked on. So don't get these two confused. So let's do some more practice questions here. So a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height, measured in feet at time t, measured in minutes. The table above gives values of the h of t, the height of the balloon, at selected times t. For t values between 5 and 15, must there be a time when the balloon is 50 feet in the air? Justify your answer. So this here is just dealing with the intermediate value theorem. So must there be a time t when the balloon is 50 feet in the air? So let's see how high the balloon was at the 5-minute mark and how high the balloon was at the 15-minute mark. At the 5-minute mark, h of 5, the balloon was a height at 40 feet. And then At the 15-minute mark, the height of the balloon was at 70 feet. So 50 is in between 40 and 70. Because if you start at 40 feet, you had to have passed 50 feet in order to get to 70 feet. So according to the IVT, there is a time t such that h of t is equal to 50 and t is in between 5 and 15. So in other words, there's just a time between 5 and 15 minutes where the balloon is 50 feet in the air. This is just how we justify it mathematically. So for part B, must there be a time when the balloon's velocity is 1.5 feet per minute? So this is where we use the mean value theorem because this table never gives us velocity ever. It's just the height. But if you recall, if you find the derivative of position or the derivative of height, that gets you your velocity, your change in position, change of height. So what we can do is figure out what's the average rate of change from 20 to 30. We can do h of 30 minus h of 20 over 30 minus 20. We get 80 minus 65 over 10, which is equal to 15. No, sorry, 1.5, because 15 divided by 10 is 1.5 feet per minute. So, remember, the mean value theorem states there's going to be, if you go back to the first page here, the derivative, the instantaneous rate of change must equal the average rate of change somewhere in the interval. So you see here how the average rate of change on the interval 20 to 30 is 1.5 feet per minute. So there has to be a time in between where the instantaneous rate of change is 1.5 feet per minute. So to write this out, just say according to mean value theorem, according to MBT, there must be a time t where t's in between 20 and 30 and h prime of t is equal to 1.5. So the answer here is yes here. All right, you can go ahead and start the practice.